Number 4, we're testing means from two different populations. Here we have a pet association claiming the mean cost of food for dogs and cats is the same. So we have our sample from each of the populations. Notice we do not know the population standard deviation. We have the sample standard deviation instead. For situations like this, where the population standard deviations are unknown, we will be using the t-distribution in our calculations. And there's also one other important thing we always need to check is whether we're assuming the population variances are not equal or if the population variances are equal. And this formula will be showing up in our test statistic. And there's two different ways of calculating it depending on which situation we have. In this problem, they're assumed to be not equal, so we'll be using this. Right here it says assume the population variances are not equal. So to start off here, what is the claim? The claim is that the mean cost for dogs and cats food is equal. The statement of equality is always going to be our null hypothesis. The two means are equal to each other. That's our null. The alternative then would be not equal to. Which one is the claim? The claim is our null hypothesis. What are our critical values? That's going to be based entirely on alpha, and we're going to use the t-distribution to find those. We have a two-tailed test because our alternative hypothesis was not equal to, so alpha of 5%, divide that in half, split it between the two tails, so we'll enter 0.025. Now the degrees of freedom. For a situation where the variances are assumed to not be equal, the degrees of freedom is the smaller of, you look at the samples, each of the two sample sizes, subtract 1 from each of the two sample sizes, whichever of those values is smaller will be our degrees of freedom. Subtracting 1 from each of these sample sizes would give us 16 and 13. 13 smaller, so that's the degrees of freedom we'll enter in here. This would be our critical value. And so our rejection region would be anything less than that negative critical value or greater than the positive version of that critical value. Let's calculate our test statistic to see if it lies in the rejection region. And the formula for our test statistic, there's also a great flow chart on this page. We're in the situation where we do not know the population standard deviation, and our variances were assumed to not be equal. So this, we're going to use the t-distribution. This is our degrees of freedom. And we'll be using this in our calculation of our formula for our test statistic. And so you'll see that showing up right here. That's what goes on bottom. And on top, we're really just going to be subtracting the two sample means from each other. This value here is going to reduce to 0 because we're assuming the population means are equal. And so to do the bottom part first of that calculation, we're doing the same thing with each of our samples. We take the sample standard deviation, square it, and divide by the sample size. And same with the second sample standard deviation squared, divide by the sample size. Add those two results together in the square root of the entire calculation. That's what goes on bottom. And on top, we're finding the difference of the two sample means, subtract one from the other. So this gives us our test statistic for our two samples. 2.951 is in the rejection region, so we will reject the null hypothesis. There is enough evidence to reject the null, and that's our interpretation down here. There is enough evidence to reject the null, which was our claim that the mean annual cost of food for dogs and cats was the same. Number 5 is similar to number 4. We're testing the mean between two different populations. The population standard deviations are not known, and the population variances are assumed to not be equal. So we'll be using this value here in our calculation of our test statistic. We'll be using this for the degrees of freedom. And here's how we'll do our entire test statistic here. That bottom part is that right there. Our situation is that someone is claiming that the mean annual income is greater in one county than it is in another county. So the claim is a strictly greater than claim, no statement of equality. So that is going to be an alternative hypothesis with a greater than. The mean from the first population is greater than the mean from the second, which means our null hypothesis then will be the complement of that, which would be less than or equal to for our null. Which hypothesis is the claim? The claim was our alternative here, that one county had a mean greater than the other. For our critical values, those are going to be completely based off of what we choose for alpha. And we'll be using the t-distribution because we do not know the population standard deviations. And this is a one-tailed test because our alternative hypothesis is strictly greater than. It's a right-tailed, one-tailed test. So finding those critical values with the t-distribution, we enter in our value here for alpha. Our degrees of freedom is going to be the smaller of subtracting 1 from each of our sample sizes. And so we would have 11 and 9. When you subtract 1, 9 is smaller, so 9 will be our degrees of freedom. And that gives us back our critical value. Excel always defaults to the left-hand tailed test, but by symmetry, the positive version of that will be our critical value, and any test statistic that's larger than that will fall within the rejection region. So now to find the standardized test statistic, this is what goes on the bottom of the calculation, and then on top we'll be subtracting the sample means from each other. And so working with that bottom part first, we take the sample standard deviation, you square it, and divide by the sample size. Do that with your first sample, and do the same thing with your second sample. Sample standard deviation, square it, and divide by the sample size. Add those two results together, and you're taking the square root of the entire thing. That goes on bottom, and on top we're subtracting our two sample means from each other, finding the difference between the sample means. That is our test statistic. 1.395 is not greater than our critical value. It's not in the rejection region, so we will fail to reject the null hypothesis, which means at the same time we're saying there's not enough evidence to support the alternative hypothesis, which in this example, the alternative hypothesis was the claim, and there's not enough evidence to support that. Number 6, there's a lot of similarities to number 5, but there are some key differences as well. Here we have the claim is that the mean in one county is equal to, it's the same as the mean income from another county. So here our claim is equality. Statement of equality goes with the null hypothesis, so our null hypothesis will be our claim. And our alternative is going to be the complement, which would be not equal to. So we'll have a two-tailed test here since our alternative hypothesis is not equal to. Just like with number 5, we have a situation where the population standard deviations are not known and the population variances are assumed to not be equal. So we'll be using this in the bottom of our calculation for the test statistic. Our degrees of freedom will be 1 minus the sample sizes, whichever is smaller. And to get the whole calculation for the test statistic, this goes on bottom. And on top, we subtract the sample means from one another. So first, to find the critical values, it's going to be based off of what we have here for alpha, a two-tailed test because we have not equal in our alternative hypothesis. We have to use the t-distribution because we do not know the population standard deviations. So we enter half of our alpha because it's a two-tailed test. We want to divide alpha by 2 to split it between the two tails. And our degrees of freedom, 1 less than the sample sizes would be 17 and 7. 7 is smaller, so that's our degrees of freedom. That's our critical value. And so the negative and positive of that, because it's a two-tailed test, and if you're less than the negative version or greater than the positive, you're further into the tails, you're in the rejection region. Now to find the standardized test statistic, calculating the bottom part of the formula first, you take the sample standard deviation, you square it, and you divide by the sample size. Do that for sample 1, and the same thing for sample 2. Sample standard deviation, square it, divide by the sample size. Add those two results together and square root of the entire computation. That goes on bottom. And on top, you're finding the difference between the two sample means. Gives us this result for our test statistic. 0.804 is not in the rejection region, so we will fail to reject the null hypothesis. And since our null hypothesis was the claim, there's not enough evidence to reject that claim.